Sure.
Yeah, it's been an honor for me to come here at WOCC to talk about our research work. So today I'm going to talk about exploring the power of pervasive sensing for IoT security and smart healthcare. And I'm currently a professor at Electrical and Computer Engineering in Rutgers University, and I'm also Associate Director of WingLab. And together, I'm also leading Data Analysis and Information Security Lab. So first, I'll give you an introduction of WingLab. I think most of you are probably already familiar with this lab. That this is an industrial university research center, mainly doing our work for wireless and information networking. And these days, we also expand to work on mobile networks, software-defined networks, and also security area and applications in VR and AR domain. So this lab is founded in 1989, and also we have about 20 faculties from ECE department, computer science department, information technology, biomedical technology, all associated or affiliated with this center. And we have about over 40 PhD students working with the professors in WingLab. And previously, WingLab has been founded by NSF since 2003 by established Orbit Testbed, which consists of 400 USRP access node. And you can see that it is on the left-hand side of the picture over here. So this is a 400 node testbed that is open across the country and also internationally for researchers to sign in and then doing research work. And we also have the control room on the right-hand side. And we're doing the research applications these days on top of the traditional wireless networking. We're looking into this millimeter wave, 5G millimeter wave, and also mobile sensing, looking to user behaviors, and Internet of Things technologies. And further along in 2018, we further acquired funding from NSF Power program together with Columbia and also NYU, that we decided to move the Orbit testbed to the city environment. So we call it the Cosmos testbed, which is the cloud-enhanced open software-defined mobile networking, aiming to deploy 5G technologies for the city scale deployment. So we plan to doing the testing and deploy the sites in the 9 large sites and also 40 medium sites in New York City and also on Rutgers campus. So this could help us to test the 5G capability, especially with ultra high bandwidth, and also the looking to the future internet, mobile edge cloud, and also the AR and VR technology. And the backbone optical networking, we collaborate with University of Arizona to help us to set up the backbone fiber optics. And to look into the research area that my group is currently working on is that we're looking into, from mobile sensing, we extend into Internet of Things, mobile healthcare domain. And also we're working on the cybersecurity and privacy, especially these days we are looking to mobile devices by looking to how to perform unobtrusive user authentication using smartphones, wearable devices to capture the gait patterns and user behaviors. And further, we're looking to connected vehicles to see that whether we can help to identify abnormal driving behaviors and also reduce driver distraction problems caused by cell phone usage. And these efforts could contribute to the autonomous driving training and also testing environments. So just to give you a few examples of the research work that's going on in my group under ECE and WingLab. So for this part, we're using a channel state information. That's a fine-grained channel information. We can we can abstract from Wi-Fi, existing Wi-Fi, to help us to do the activity identification. So today, in the later part of my work, of the talk, I will talk about how to utilize this fine-grained channel state information to perform vital signs monitoring. So starting from 2013, that we are looking to how to utilize the Wi-Fi signals with the detailed signal channel signatures to help us to starting looking to activity identification. So this is more like a coarse-grained activities that we're looking at in the different domain inside of home environment and also elder care environment. And further, we also utilize the Wi-Fi signals to look into whether we can determine there are any suspicious object inside of luggage. So this is a more recent work that we obtained the Best Paper Award in the CNS, and also this has been licensed by a venture capital bull run. And they also established a startup company called First Responders Technologies around this technology. So currently we're working closely with them. So the idea of this work is that by using the channel state information, whether we can determine if there are any weapon inside of a bag or any liquid inside of a luggage. Because these days, the terrorist attacks that we've been gone through that involve that the attackers, they hid their weapons inside of the luggage, or they carry homemade bombs, those composed of metals and also liquid chemicals. So we feel that this line of work actually has a very important societal impact, and it could change. It could change the game. It is a game changer on top of the current X-ray-based security systems. Because nowadays in airport and many other places, the security system is mainly X-ray based, and the cost is high, and also so it prohibits the large-scale deployment. So if we can utilize Wi-Fi signals to detect the dangerous objects inside of luggage, this basically could become a game changer, and also can help to perform the larger scale deployment. And also it is a portable deployment that could be set up in sports stadiums, theme parks, public schools. So it could have a broad usage along that area and largely improve the public safety concerns. And we're also looking to by how to utilize acoustic signals to perform attacks. So we see that if you put a smartphone close to a keyboard, because nowadays the smartphone is equipped at least with two mics. Some smartphones can even equip up to 4 mics. By use that information, when people are typing on the keyboard, actually the smartphone's microphones could pick up the keystrokes and then infer in which keys the keystrokes happened. And by using that information, we can perform millimeter level audio localization and then infer the password, PIN number, and also even the email content of people's when they are working in a public area or in a conference room to type on their keyboard. So this work is related to the cyber security area that I've been working on. And also I talked about we have work in the connected vehicles area. So the work that I'm showing here is that we show that by using the wearable devices wear on the drivers, or by implant an IMU sensor on the driver's steering board, we'll be able to collect unusual events. For example, what are the unusual events? That is when it's raining, okay, when the road is wet, or when it's snowing, when the road is slippery. And also sometimes in the city environment, when the pedestrians just pass the road suddenly and cross the road suddenly. And also you can have animals all of a sudden they jump out from the road. So all of these are the unusual driving behaviors. And the data collection of unusual driving behaviors are very important, because when you train the autonomous driving environment, usually, okay, you need to train the system is that how the autonomous driving, that they can react to the unusual driving scenarios. Because on the normal situation, it is fine, okay, autonomous driving is not a problem. But when there are some situation happened, when the road is slippery, when there's an animal, all of a sudden they jump across the street, or there's a pedestrian, all of a sudden they across the street. So these are the situations when you need the driverless car to react in a timely domain, and then have the right decision. So collecting the unusual events is a critical component as to serve as the training part for the autonomous driving scenarios. And further, okay, I show that we have some workers that we all related to using the sensors, okay, to show that how you can perform a virtual fitness assistance, and also even by using the PPG sensors on your smartphone, we can perform gesture recognition and further to do a sign language interpretation. And also this shows along some of the work that we'll use in the RFID tags to perform the gesture recognition and also 3D body tracking. So a lot of now work have industrial impact. This shows here showing some of the work that have been licensed. For example, the work that I talked about, we started by using the channel state information to do activity recognition that we call it EIs. And this work has been licensed by a real motion analytics company. And also we have some other work, which is the Vibrite work that I'm going to talk about it today, that currently we're cooperating with Allegiant, which is a company doing the providing security products and also user authentication solutions for home and business usage. Okay, so looking to the main part that I'm going to talk about today, that is we look into how to use sensing related to the physical vibrations. Okay, when we look into pervasive sensing, okay, it includes RF sensing, acoustic sensing, and vibration sensing. So usually these are the three main areas people are looking to. And these days, vibration sensing actually it's becomes more and more important because it only involves low-cost sensors, and also the power consumption is very low, and it can enable a broad range of applications. What we show here is that this is the PCB board that is being utilized, being designed and also made by our group. And we use a piezoelectric sensor, which is very low cost, only cost about $5. And you can see that when we connect it to a smartphone, we can actually extend the whole keyboard, okay, to the solid table, and then showing that you can turn the small touch screen into any solid surface, and to enable, for example, virtual keyboard, multi-party meetings, and also many other applications we show on the left-hand side. One is to perform user differentiation or user identification, where you have this vibration sensors being installed on the door panel, and to do all kinds of fine-grained localization. So focus on the work I want to do is that I want to show you that by utilizing this low-cost sensors to perform vibration, we'll be able to perform the finger input authentication on any solid surfaces. So this work has been published in the ACM CCS, which is among the top 4 security conference. So we see that today the trend of user authentication is that people are more looking to the low cost, low power, tangible user interfaces in addition to your PIN number based user authentication. So I show a couple of examples here. Okay, people have shown that you can utilize a ring that you can wear on the finger and to perform capacitive touch authentication. And also you can use a pen, okay, pen-based, okay, user authentication. We call it a smart pen based user authentication to utilize the circuit. Basically, it's the circuit-based on touch screen user authentication. So what we like to see is that current work, they're more looking to the electric conductivity or specialized sensing pad. In our work, we like to see that without utilizing a specialized sensing pad, is that possible we can support user authentication on any surface? So we've already seen that this is shown in the Mission Impossible movie. You see that the actor, they put their palm on the driver's door, then you'll be able to authenticate and then start driving the car. So this is now eventual goal that we like to achieve by using the physical vibration-based user authentication. So the idea, okay, to do that, okay, is that we like to have this basically attach the low-cost sensors on any solid surface, okay, on your, for example, on the door panel or on your desk, so that if you sign a document, okay, in your desk, it should be signed in your office. You could not bring it home to sign it. Your authentication will fail. And for a high-rise apartment building, only the residents could go into the door. Currently, we usually utilize intercom or card-based access. And by utilizing this vibration-based signal, you'll be able to authenticate when you put your palm in the high-rise building entrance, and then you can be let in if you're a legitimate resident in this building. So the basic idea that we're using here is that you see that if we have a vibration motor and then a low-cost vibration receiver, you will see that when you have touch on the solid surface, it will disturb the transmission, the vibration signal transmission along the medium. Here it is a table or a door panel that we show here. And by changing the direction and changing the location, when you touch on the table, okay, we'll be able to capture, first is the location, and the second is the human biometrics, because different people's finger size, touch force, and also the finger skeleton is different. So looking to the physics side, okay, what we try to capture, okay, it is the behavior, both the behavior and also the physiological characteristics that we try to capture and extract when the finger touches the solid surface. That is your vibration signal will get reflected and also have interference when they pass through the medium and then go to the receiver. So here shows the system overview, and the right-hand side, it is the demonstration that we show that how a student can come in and then perform user authentication. So what we do is that for the left-hand side, well, first, once you collect the vibration signals, we're going to perform data calibration. And then we perform a feature extraction and selection. And here we're looking to the spectral point-based feature, looking to the frequency domain. Okay, and then we further, okay, using machine learning techniques to help us to derive the grid points or the gesture segmentation. So currently we show that how we can, the demonstration we just showed to you is that how we start this application by showing what we can utilize for a pin number based approach, log pattern based approach, and eventually it's going to be the gesture based approach. And the student have been shown that currently, okay, what they do is that they put a gesture or we say a small signature on the table, they'll be able to access the table's drawer and also access the laptop on the table. Okay, so for some technical details is that, first of all, for the vibration signal design. So we designed the vibration signal in the high frequency domain, which is between 16 kilohertz to 22 kilohertz. So in that range, the signals are not sensitive to human ears. So it is not a disturbance to human ears when the authentication system is running. And we have this repeated chirp vibration signals being played by the vibration motor. And further along, okay, when you receive the vibration signals, we need to perform the vital signal synchronization. So what we usually do is that we need to synchronize the received vibration signal with the sending motor signals, and then we perform cross-correlation. Because sometimes we also encounter, in the real systems, we also encounter the clock drift problem. And we also find some ways, some strategies to help us to actually correct the clock drift. And furthermore, okay, we look into the received vibration signals in the frequency domain by using sliding window techniques. What we do is that we look into the spectral points, because we find that the spectral points are most sensitive, okay, to the small changes of finger touching, because your finger is going to touch or write in the different locations on the solid surface. And further, okay, in addition, we utilize the MFCC techniques, which is the male frequency capture coefficient. MFCC is a widely utilized technology in speech recognition, and we find that it also can capture changes associated with vibration surface. So what we do is that we also utilize MFCC in addition to the substrate point to help us to look into the fine-grained location estimation. So here shows our steps. Okay, when we look into the substrate points, it can help us to determine those maximum points are actually could be the grid point. So what we do is that we're further, okay, we have a few strategies, mechanisms that we derived in this work is that we derive the grid point index traces, and then also, okay, perform the grid point index filtering. Okay, that help us to identify the consecutive, okay, consecutive grid point indices, and then further to derive either the pin sequence or lock pattern. So this is the experimental setup that we have in our lab. As I mentioned before, that the right-hand side, this is the piezoelectric sensor that is as the receiver. And what we have is that we made the PCB board. We designed the PCB and then made it outside. And then this is our piezoelectric sensor as the receiver, and then the amplifier board. And then we have a small vibration motor. So this is the testing area that we have. We're starting with the pin number testing. And we also go to the block patterns. And eventually, we're currently working on the just the gesture testing, when you just swipe your fingers, okay, on the solid surface. Okay, so this part of the work, okay, we show that how to utilize vibration signals to help us to perform low cost and low power tangible user authentication that basically can turn any touch screen into a solid surface. And what we have is that we can utilize this kind of method to authenticate on any solid surface. So we call it ubiquitous surface on door panels, on the desk tables, desktops, and also on the eventually on the vehicle doors. So next, okay, I like to talk about our second part of the work is that it's also a part of pervasive sensing, but it turns into a different angle is that as I talk about, to utilize fine-grained signal information to check vital signs during sleep. So this belongs to the smart healthcare work that we're looking into by using a mobile sensing. So why sleep is important? Because we all understand that without a quality of sleep, it could cause a lot of problems. And also the irregular sleep patterns can also help us to determine any possible health issues. Most importantly, for example, if we perform vital signs monitoring, we can determine if this person has apnea problem. Apnea problem is that when you sleep in the middle of the night, it is possible that part of your breath, you can stop your breath for like 5 to 10 seconds and then it resumes. So for a person who suffers from apnea, for the sleep apnea problem is that even when they sleep for long hours, for example, 7 or 8 hours, after they wake up, they still feel very tired, okay? Because the problem is that their brain, okay, did not have enough rest, and also because of the lack of oxygen for sometimes, it can be dangerous, okay, to the people's health situation. And also the vital signs monitoring during sleep can also monitor any heart attack problems, and even can capture the early signs of depression problems. So the existing work of looking to the vital signs monitoring, it is sensor-based. Okay, the most common method is that you go to the hospital, okay, and then the doctors and nurses put many tags attached to you, and then you sleep there. You spend probably a couple of nights over there, and then they capture your vital signs and then perform your health state evaluation. The problem is that in this kind of testing, it is high cost. And also usually when you only go to the doctor to see this problem is that your problem is quite severe, and then you know that you encounter the sleep apnea problem or a heart problem, that you have to go to see the doctor, right? And in our case, okay, in the case that we want to look at is that we would like to have this as a long-term monitoring, low-cost well-being monitoring at home, that without going to see the doctors first, that you can have some ideas whether you have any irregular sleep problem. So this can actually help to identify early sign of sleep apnea problem, and also the heart problems, and even diabetes problem. So at home nowadays, okay, one possible way is that you see in the middle picture that you can have a chest band, okay, across you wear across your chest, and also wear the oximeter at night to measure your heartbeats and also your breathing rate. But you can see that it is still very inconvenient. Okay, while for today's wearable devices, we're looking into Fitbits and smart watches. It can capture your heartbeats, but it cannot measure your breathing rate. Breathing rate is especially critical to pick up the heart problems and also the sleep apnea problems. And also we know that many people, they do not wish to wear smart watches and also wearable devices during their sleep. So in the research area, okay, what do we like to do? Okay, in RF-based sensing, people feel that if we can utilize the existing RF sensing, so for example, we can reuse the Wi-Fi signals, because Wi-Fi have been deployed widely these days in many areas, and especially in the home environment, it is prevalent. So people are trying to see that, okay, at the very beginning, we're looking at whether they utilize specialized hardware, for example, USRP, FMCW radar to perform RF-based sensing to try to pick up your breathing rate and heartbeats without attach any devices on the user. We call this line of RF sensing as a device-free sensing, or we call it as contactless sensing. Okay, and the problem for this initial research is that you have to deploy specialized hardware, okay, in the home environment. So what we like to see is that whether we can provide this contactless and long-term monitoring, okay, without deploy specialized hardware and do not need to customize the hardware. So what we like to do is that we look into the off-the-shelf Wi-Fi devices. So the idea is that we show that in our earlier work, right? Wi-Fi signals, it can capture your activities during the day, whether you're working in front of your computer or you're washing dishes or you spend time in the bathroom. For all those call-screened activities, Wi-Fi signals got disturbed and then can pick it up easily. But for breathing and heartbeat, actually they only cause minute body movements, okay, as we show here. Okay, whether the Wi-Fi signals could capture this kind of small body movement, okay, this is the biggest challenge when we conduct research in this area. So from our initial study, we see that, okay, the fine-grained channel state information actually could, okay, detect the minute body movement. So in the bottom figure, okay, it shows that this is in the time series, and you have the channel state information amplitude as shown here. It shows 4 subcarriers, and with these 4 subcarriers inside of the channel state information, we see this repetitive patterns. So this repetitive pattern are actually caused by the breathing rate of human. Okay, so this gives us some lights. So again, okay, we built this the development system, okay, that is a combination of the signal processing and machine learning techniques that we have. And the right-hand side, okay, also shows the demonstration, okay, of the student that they're participating in these experiments. We show that when people are sleeping on the bed, and then we have the iPad or laptop placed beside their bed, okay, how the Wi-Fi signals here, okay, could be captured to monitor people's breathing rate, okay, and heartbeats, okay. And in the system, okay, what we show here is that we show how we can determine, okay, when there's a single person sleep on the bed or there are 2 persons situation, okay, and what kind of learning methods, okay, we can utilize in both the time domain and frequency domain to help us to determine the heartbeat and also the breathing rate at the same time. So people may argue that, okay, for the heartbeat, we can utilize the smartwatch to pick it up easily, the PPG sensor on top of that. That is true, okay, but as I pointed out, for the smart watch, actually you cannot pick up the breathing rate, right? And once you pick up the breathing rate from the channel state information, you also would like to utilize the same modality to pick up the heart rate, because only when you have the same modality to pick up the biometrics, they could be compared directly, and they could be utilized as an indicator of your health factor. Okay, and we also show that, okay, as a side product of vital signs, okay, well, very easy for us to detect the sleep events. Those sleep events, which we call the call-screened sleep events, okay, those are the ones that cause a large movement in the channel state information. For example, when you go into bed, and when you turn over during your sleep, and also you will change your sleep posture, and then you're snoring at night, and then you get up, okay, to go to the bathroom. All of this body movement, they cause large disturbance in the channel state information and are much easier to be captured. And by looking to, the breathing cycle identification, this is the most important part. So the problem is that there could be fake peaks. We show that in the time domain, in the CSI amplitude, we see the repetitive patterns, right? But it could be some fake peaks, caused by transient environmental changes. For example, when you're sleeping, all of a sudden the air conditioning is on. So for those kind of noise can also cause small disturbance in the wireless signals. So that can be exhibited as your peaks in the channel state information. So what we do is that we understand that there's a minimum distance between two neighboring peaks based on the human's maximum possible breathing rate, right? By use that, it can actually help us to filter out some of the fake peaks, And also, we also have a verifying window, to help us to move along and then to help us to determine, what is the signals, around this peak, whether they are all lower than this peak, to determine if this is a valid peak or it is a faked one. So here, shows some of the evaluation results that we have when comparing with the reference signal, which is a new log respiration monitoring logger, a commercial product, which is showing as the red curves here. And then the blue cross here are the detected local peaks, in the different subcarriers in the CSI. And you can see that the results are pretty consistent with the reference signal. And later on, we further utilize how to combine the breathing cycles with the variance of weight to help us to have a more accurate result. And further along, to track the heartbeats simultaneously, what we do is that the good thing is that the heartbeats and breathing rate, they have non-overlapping frequencies. Basically, the breaths are usually, people have is 10 to 40 breaths per minute, while for the heartbeats, it's during the sleep time, it is usually 60 to 100 beats per minute. So this helps us when we look into the frequency domain. When we look into the frequency domain, by looking to the substrate distribution, it helps us to determine, what is the estimated heart rate. So we also conducted experiments, with different sleeping postures, as shown on the left-hand side. These are the different sleeping postures. We can see that the curl up is the most popular one. Sleeping posture has about 40%, and also some people sleep on their tummies. It's about 7%. So we show that in a bedroom environment. So we have like 3 different setups. The first one is we see it is ideal scenario where you have the transmitter and the receiver, just around the bed. And then the second setup is a more typical scenario. It's it is a longer distance. For these 2 bedrooms, you see that it is a diagonal distance for the access point and your laptop or your iPad or your smartphone. And for the third scenario, it's a more challenging scenario, is that the access point is not inside of a bedroom, it is in another room. So you have walls in between. So here I didn't show our experimental results, and I just want to tell you that from our experimental results, we can see that our results are compatible with the off-the-shelf oximeters that measuring the heartbeats, and also the respiration monitor that measuring the breathing rate. And this work, okay, basically we want to show you that is that by using the RF sensing, when we call it the device-free sensing, we'll be able to utilize the Wi-Fi devices to help us to show the feasibility to perform vital signs monitoring during sleep. So what's next? Okay, I'd like to talk about some future work. Okay, I think it could be exciting that bringing in the pervasive sensing area. So we talked about, okay, I've shown you, okay, what we've done. That is that to do the user authentication, we use vibration signals, and also some of our recent work, we see that user authentication, we can utilize the gait patterns picked up by the wearable devices. And here, okay, we want to show you is that you can utilize, okay, for example, the regular camera, and the flashlight, it can, you press your finger on it, the reflected light could pick up your heartbeats. Okay, then we can perform the continuous user authentication. Excuse me, use the heart-based continuous user authentication. Sorry about it. And then this could be utilized, okay, in your phone, and also, for example, smart refrigerator. Okay, all those scenarios when the fingerprinting method is not available, and also in low-end phones, if you do not have a fingerprint method, this could help you. And also, this could serve as a second factor on top of the face-based recognition. And also going forward, okay, there are so many voice recognition systems or voice assistant system in your home that can help you to control everything in your smart home. Okay, it knows your daily schedule. Okay, it controls the appliances at your home, lamps, temperature, and also it keeps your calendar information. So there are many sensitive information actually stored in your voice assistant voice assistants. So there could be many security issues. Okay, people can basically ask questions for the voice assistant system and control the temperature in your home and know the calendar, know your schedule of your team of your home family members, and also it knows the schedule of your kids and when you're going to pick up your kids. So there are many security issues that in this domain, and currently we're applying the adversarial machine learning techniques to help us to build more secure speaker recognition systems that could be integrated together with the voice assistants. And further along, okay, we're also going to look into the security issues in the augmented reality system. So we envision that in the augmented reality world, right, you have the real world combined, okay, with the augmentation inside, right? So this can actually provide you many information, is that you know, okay, which store had what kind of advertisement, had what kind of coupons that you get, right? So this is very useful, okay, for you, right? And however, okay, when you're looking into this, this could also have many security issues, right? So people wonder that, okay, user identification, right? We like to see that whether you as the user or the other person, when they contact you through the augmented reality world, how could they be authenticated? Okay, and here we think AI actually will play a great domain here, because there's going to be tremendous items in the augmented reality world for us to perform training. Okay, and by using the traditional way that we perform regular data collection and then to perform training, this will not be sufficient and also could be error prone. So the artificial intelligence will play a great role here to help us to perform training, and further, okay, it will help us to determine the user authentication scenarios. And also in augmented reality world, you know, a lot of times you have this navigations, auto navigations that you just saw, right? So for the auto navigations, if for attacker come in, the attacker told you that there are no cars, okay, in this block, or they take away some of the cars, okay, vehicles in this block, that could also cause problems when you use navigation in the augmented reality area. So you can see that there are many authentication security problems here that we can look into. Okay, so this pretty much conclude my talk, and this my some of the collaborators that I have that are working together with me, and those are the faculties that we've been working together, and some of them are my previous PhD students, and now they are faculties also working in the academia, and also I have many excellent students working with me together. Yeah, so I'd be happy to take questions. Thank you.
Thank you.